Yeah, I'm Natasha Abrams. I'm a grad student at UC Berkeley, and I'll be talking about bias and fitting simulated light curves from PopSyCLE. So first I'll give a brief overview about what goes into a fit and what are some sources of error that can be in one. So first we start out with data. In this case, we'll be using simulated data since we want to be able to measure the difference between the input and the output for, from our fits. Then cadence goes in, which can cause issues because it can cause you to miss features in your light curve. There's noise in your data, which in general can be scattered, but there can be correlated and uncorrelated noise. And if you don't include the non-Gaussian, if there is correlated or non-Gaussian noise in your light curve that's not included in your fit, this can cause bias. In this case, we'll just be considering Gaussian error though. And then there's the parameters that are give you your microlensing event. We used PopSyCLE, microlensing population synthesis code, to generate parameters for fits, binaries, black holes, all that jazz. But of course, there could be errors in your galactic model that can cause issues. Next, we actually do the fit. In this case, we use nested sampling based model. This is particularly good for microlensing since it's a highly degenerate parameter space, and that way you can examine the entirety of the parameter space for your events. Because this is a likelihood, which is the probability of getting your observations given the model. There's also priors in your model that tell you the prior distributions of the parameters that you expect. So of course, there can be incorrect priors that give bias. There's the actual model. There can be numerical issues in those models. And there can also be mismatches between the true microlensing event that you're trying to fit and the type of model that you're fitting it with. And finally, there's the interpretation. There's the posteriors that show you in fully gory detail all the different parts of your results. There's also best fit quantities that might be easier to work with when you have a whole host of microlensing events. But that may not capture all the degeneracies in the parameter space. In this talk, I'll be focusing on the parameters, the input distributions from PopSyCLE, from model mismatch and prior mismatch, how that affects your fits, and interpreting the best fit quantities. You can see Goldfish et al. 2022 for more exploration of the non-Gaussian noise and model mismatch using nested sampling. So we generated the light curves using PSPL and PopSyCLE parameters with oval ground-based photometric noise, using cadence and noise properties based on oval EWS. These are some examples of light curves that we simulated to be fit. And so we want to find the detectable microlensing events that were fit well to PSPL models. So we determined the goodness of fit using chi-squared. We calculated two different chi-squareds, one a chi-squared based on a line, or just a sigma clipped mean. We did this because we don't want to include things that fit well to a straight line, which may be the case if there's a microlensing event that occurs during a big gap in cadence, or when it's very faint and there's a lot of scatter, and so the signal doesn't make it above the noise. We also looked at the chi-squared compared to PSPL model, and we want to keep those that fit poorly to a straight line, and a good fit to a PSPL model. We did that by looking at the reduced chi-squared probabilities above the 99th percentile or below the 99th percentile. And so here's a few different scenarios that I'm going to walk through for the rest of the talk. So we looked at when we have PSPL plus parallax input with just fitting with the PSPL model, a PSPL plus parallax input fitting matching PSPL plus parallax model, looking at a uniform prior in pi-e, and then having an input being PSPL and binaries with parallax, everything fit with PSPL with and without parallax. And so I'm gonna have this key in all of my slides saying what are the input and fit. So for a PSPL with parallax fit, input and a PSPL fit, we found that the overall shape of the T distribution is unchanged, but there can be significant differences in individual events. So on the left, you can see the histogram of the number of events as a function of the Einstein crossing time, and that the distributions look similar between the fit and the input distributions. But on the right, you can see the T fit values minus the input, and that there are significant differences over 50 days. But these differences should be captured by the error bars for the most part. So these are violin plots that I'm going to be showing throughout the rest of this talk with the bias factor on the y-axis. So that's the fit value minus the input value divided by the error in the fit. And the distributions are the actual distributions in the bias factor. On the left-hand plot, the horizontal line is the median of that distribution, and the vertical lines are the standard deviation. And you can see that for the T distribution here, that the median was very close to 0, and so it's within one standard deviation. So while there are events that are have significant deviations, they're on a whole the distribution isn't biased. There are, however, significant outliers, which are what's marked in those red lines on the other plot, where the one on the left is just zoomed in, or the one on the right, where there's significant differences. And this could be because there's large differences between the fit and the input values, or that we're underestimating the errors in the fit, or both. So next, when we have the input PSPL plus parallax and the fit PSPL plus parallax, we see that pi e is actually biased as a function of pi e. So this is generated, the priors are based on PopSyCLE with the pi e and pi en. And so that's the same distribution as the input parameters that we put in. And you can see though there's a significant difference in the input and the fit distributions on the left with the histograms, where the orange is the input and the blue is the fit. And then we can actually plot the bias factors in bins of pi e. This is the same as the other plots, but with just we're binning in pi e, and you can see that for larger pi e values, that the input values are larger than the fits, so it wants to push towards smaller pi e, and vice versa for the other side. However, we don't actually see bias within the errors for the other parameters, the T, U naught, G naught, MyBase, and BSFF, but there's certainly potentially optimization that we can do for the priors in these to potentially explore the effect of those. Because we can see that using an unrealistic parameter can lead to more bias, both in the parameter itself and in other ones. So this is when we tried a uniform prior in pi e, and you can see in the left here that the number of events is a function of pi e. The distributions are just totally different, where the orange is the input and the blue is the fit. But not only does it just affect pi e, it can also affect the Einstein crossing time. You can see that the fit and input distributions are significantly different here. So now moving on to the inclusion of binaries. So when we did the PopSyCLE simulation with injecting binaries for a ground-based optical survey type simulation, we found that more than half of the stellar and compact object microlensing events have at least one binary, with either binary lens, binary source, or both. We then fit all of these with a PSPL model, and we found that the majority of the binary events are fit well to this model. So this is in this case PSPL with no parallax, and we found that about 7% were fit poorly to a PSPL model. We also found about 1.5% that were PSPL events fit poorly to be a PSPL model, and this is for two reasons. One is if they had a very large parallax signal, and the other is if they were pretty faint with a lot of scatter and the fit just tagged on to the wrong signature. We also see a similar amount of bias in the distributions between PSPL and binary events. So these are the histograms of the number of events as a function of P for all events, PSPL, and all the binary events. And you can see that the distributions between the fit and the input are relatively similar between all. We did, however, see significant bias in pi e. So the binary lens case, in the binary lens cases, we see that the input pi e is less than the fit one, and so it wants to push towards larger values of pi e. So thinking about Rubin and Rubin beyond, our minimum baseline magnitude is going to change. And we actually see that in the intrinsic case, so this is not fitting, the intrinsic fraction of binaries is actually dependent on the baseline magnitude sensitivity. So the way to interpret this plot is that blue is point source point lens, orange point source binary lens, green binary source point lens, and red binary source binary lens. And each of these represents the fraction of microlensing events that fall into the respective categories. And so at any given vertical line here, vertical slice, that's the minimum baseline magnitude cut. And you can see the fraction of microlensing events at each of those values. And so for like current ground-based surveys, you can see that more than half of the microlensing events include a binary. But as we push towards baseline magnitudes, you can see the actual fraction of binaries decreases. But we still have a lot of work to do with actually fitting the microlensing events and such. We can also look at the potential of astrometry we can look at the potential of astrometry to help us with this. And you can see up here a point source binary lens, and down here is a point source point lens, where you may not be able to distinguish from the light curve, the binary lens is the actual binary lens case. However, there are significant differences in the astrometric signal. However, there's a lot of work to do in terms of adding in the Roman errors, trying to fit, and looking systematically through all the light curves and astrometric curves to see what fraction are potentially distinguishable in that way. But this can just show a bit of the potential. So in summary, the overall shape of distributions may match even if there's significant bias in individual events. The priors can have a large impact on the bias and output of the distribution, both for their own distribution and other distributions that are being fit. Most binaries are fit well by a PSPL model, and intrinsic binary fraction is dependent to the baseline magnitude sensitivity. Thank you.
So in your earlier slide where you were showing biases in the parallax results, the first one you showed, you said that the models tend to underestimate the biases. And then you showed one with a uniform prior. So in the first instance, where you were underestimating the parallax of the models, what prior did that?
Yeah, so that was using a prior based on the simulated events from PopSyCLE. So we took the simulated events from PopSyCLe and looked at the mean and standard deviation of the pi e and pi en and plugged those in for the prior.
Okay, and then the second one's just swapped a uniform prior.
Yeah, just to explore, well, actually, in fact, I presented them in the opposite direction, but we actually had tried the uniform prior first, just as, a test, and then we saw that there was that significant bias, and so we went in and actually tried the more realistic prior.
So, but actually, how do you pick your events, which just fitting the best likelihood, or MCMC with using those bias?
Yeah, so we used a nested sampling routine, which is similar to MCMC, but instead of having it's less likely to get stuck in like local minimum.
Yeah. But anyway, so you use the price. But have you compared what happens if you just use the best likelihood? If you still get the bias or not?
So we use. So from the nested sampling, you can get out the maximum likelihood, value, and that's what we were using as the like. The actual values that we were looking at. We are still working on like doing the thing where you can actually add up all of your posteriors to you know, have a more complete distribution, but yeah, but we can talk more.
Yeah, so maybe we can.
Yeah.
There was, so Scott.
In the case of the linear prior for, if you go back to that figure. So your posterior looks like it's.
Yeah.
Your posterior. Like prior is, if I understand, so isn't this just the case that you don't have very strong constraint on the parallax, and so you're recovering your prior?
Yeah, so if we. That could definitely have an effect, but if that were the case, then like when the input distribution in this should be the fit distribution, and that's not what we're covering. So we're definitely there's definitely more exploration to be done.
But
Yeah.
but the first order is probably just.
Yeah, so we've looked at the distribution as a function of TE as well, this like bias factor. And so you would think that like for shorter duration events, maybe you're more likely to be more biased because like it's just gonna follow the prior. And that's actually not what we're finding. We don't see a bias as a function of TE for either this one or the uniform prior.